Hello, everyone. This video explains some questions from practice exam 3, actually regarding to the thermal part. Okay, so now let's look into the questions. Let me share my screen. Okay. Okay, so here we go. Okay, so for question number 12, okay, so if you look at that clearly, that's a size is calorimeter. Okay, so as I also mentioned, right? So I will put wording such as this. Okay, a calorimeter is built for constant volume or constant pressure. You have to recognize constant volume is talking about calorimeter, and then constant pressure is talking about coffee cup calorimeter. Okay, so I'll do that. So make sure you know about that detail. Okay, so again, back to this question, it's telling us there's a bomb calorimeter and has heat capacity. Okay, so then again, that heat capacity is for what? That's used color. Okay, so heat capacity. Okay, so that's the information for our calorimeter. Okay, so that's the heat capacity for our calorimeter. Okay, so then that's what we're going to use. Okay, and then saying 1.109 grams of sample. That sample was burned in the calorimeter. Okay, so the sample is our reaction. Okay, so then I have information mass for my reaction. Okay, so of the reaction. So you know information about the reaction. And then saying, right, so when it burns, the temperature increases by 2.22 K. Okay, so then again, that's right. We can observe, I'll do the observation for that for our calorimeter. Okay, so then there's also the information temperature change for the calorimeter. Okay, so and then it's asking us about calculate the energy of combustion of 1 mole of the ethylene. Okay, so then again, that's looking for energy, right, about the reaction. Okay, so then clearly, as I said, right, so there is a relationship. We'll assume, right, the heat change is only between the calorimeter and your reaction. Okay, so and then from calorimeter, we also learn this, right? So the energy change of direction will just equals the Q of direction due to, since it's built for constant volume, therefore work equals 0. So then delta E, the energy change of direction, just equals the heat of direction. Okay, so remember that's constant volume. Okay, so that's why work equals to 0. Okay, so then we can do this calculation. Okay, so it's hard for us to look for information for the reaction, but we know the relationship between the reaction and the calorimeter, they are the opposite relationship, right? One absorbs, the other one release. Okay, so then that's why they have the opposite relationship, as we keep on saying, right? So this negative sign simply telling us, right, they have the opposite relationship. Okay, so now that's what I have, and then we have information for the calorimeter. So we can use the heat capacity times the temperature change. So that would be 2.47 kilojoule Kelvin times temperature change 2.22. Okay, and also notice the wordings that increase by, right? When we say by, that means the difference already. Okay, so that's why we're given with one temperature. Okay, so because that's already telling you the temperature change. Okay, if you do that calculation, we'll get 5.48 kilojoules. Okay, so then that's the heat that calorimeter absorbed. Okay, so then we know the reaction is releasing heat. Okay, so then again, if we know that, we can simply get to the Q of the reaction will equals negative Q of the calorimeter. So that will be negative 5.48 kilojoule, again representing, like, our reaction is releasing heat. Okay, so then that's what I have. And then again, when we get this number is based off what? Burning that point. This is a matching, or this is coming from burning 0.109 grams of the ethylene. Okay, so then we wanted to know what? Every 1 mole of ethylene. So you go, okay, I think what do I do? Well, I know what to do from this point, right? Okay, so then the delta E equals to Q of the reaction. Okay, so now that Q, we wanted to per mole. Okay, so now we need to deal with that. So then that'll be negative 5.48 kilojoule. This is coming from 0.109 grams. Okay, that equals to how many moles? We can simply do that calculation. Every 1 mole of ethylene, which is C2H4, you go to your periodic table, should be able to calculate the molar mass. That's 28 gram per mole. So grams got cancelled. After this calculation, we get kilojoule per mole. kilojoule per mole, energy per mole, right? So then that's our calculating. Okay, so do this calculation, we'll be able to get to the final answer. Okay, so if the question is asking us, right, so that'll be negative 1.41 times 10 to the power 3 kilojoule per mole. The question is asking calculate the energy of combustion of 1 mole of ethylene. Okay, so that energy is right is really right or be releasing 1.41 times 10 to negative 10 to the power 10 to the power of 3 kilojoule per mole. Okay, so then that's the question 12. Okay, so that's that. Then let's look at the next question. Okay, so next question, if you look at it, give you a reaction equation, ask you which ones be true. Okay, so reaction is exothermic. So which means Q will be negative. Okay, at constant pressure, Q equals to delta H. And then again, delta H is negative given from question. So then I'll be okay. So the first statement is true. Okay, so negative sign is indicating the reaction is exothermic reaction. Okay, the next is asking us 0.5 moles of sulfur. Okay, so right over here, okay, we'll be releasing 148 kilojoules of energy. You go, how do I find out information about that? Okay, so again, that balance equation, that's what's helping us, right? So that's telling us every 1 mole of sulfur, you go, where's that one? Remember coefficient, if we didn't write it, it's 1 to 1 to 1 to 1 ratio. Okay, so then we know every 1 mole is 1 mole of sulfur releasing that negative, releasing 296 kilojoules. But if we just use simple and sign to represent, it will be negative 296 kilojoules. Okay, so then that's for that. And then now we know I have 0.5 moles of sulfur. So we set this up. Okay, then for 0.5 mole, I'll release 148 kilojoules. Okay, but then again, that sign just telling us, right? Releasing. Okay, so release. We use words to describe it, then that represent the sign. Okay, so then the second one is also true. Next one is also asking about sulfur, but now you see what it is, right? Okay, so if it's about sulfur, what do I do? Let's do number 3. And there's some space. Okay, so for number 3, okay, so we know from balance equations mole relationship, right? So then we need to turn that 32 grams sulfur, okay, go to periodic table, is 1 mole is 32 grams. That cancels out, so I have 1 mole of sulfur, and the 1 mole of sulfur is matching with what? That 296. Okay, so then let's go. It's 1 mole of sulfur is matching with negative 296, which also means releasing 296 kilojoules of heat. Okay, so that cancels out 296 kilojoule. Okay, but then they're asking us in joule, because that's easy. That'll be 2.96 times 10 to the power 5 joule. Okay, you simply did a unit conversion, so that's good. That's right. Okay, again, the negative sign, we use release the wording to represent it. Okay, so that's also true. Okay. Now we learned, we found out all the statements are true. Okay, so the next choice. Okay, so that's for that one. So now let's look at the following question. The following question is about enthalpy change for a reaction. Okay, so if you look at this, you go, right? I'm given with several equations, 1, 2, 3, and I have a final equation right over here. Okay, so then that's what I'm looking for. As I said, this type of question, what do? Is that we have to look into the given reaction and then what we're looking for, and then see how they're related. Okay, so then you go, okay, so let's look for CLF. Okay, so you go appears here and it's on the left side. Okay, so then that's good. Coefficient doesn't work, but then let's leave it. Okay, and then that's for the first thing we found out. Okay, so fluorine. Here you go. Okay, I found it from equation 3. I also on the right side. Okay, and then moles, if you look at it, from my given equation, both have 2 moles, and then for my final equation, I have 1. You go, if at a certain point I can divide it by 2, that can solve the issue, right? Okay, but then let's leave it. Okay, so because they're on the right correct side. Okay, and then let's see what else we have. We have ClF3. Okay, where I can get that? I can get from equation 2, but I want it as a product. Look, that's on the right side of my reaction. I want it as a product. but it's given as a reactant, okay, on the left side, okay, so then go, I have to do something, right? I have to reverse my equation, okay, so then that's what we're gonna do, some actions, right? We're gonna reverse equation 2, then let's reverse it, okay, so now I have Cl2O plus 3 of F2O, then I got 2ClF3 plus 2O2. Okay, so I reverse it, I'll call it as equation 4, and equation 4, the delta H. Since I'm reversing equation, delta H will add a negative sign up front in comparison to equation 2. Okay, so original one should be positive 341.1. Now it's going to be negative 341.1. Okay, kilojoule per mole. Okay, so then that's what I have. Again, the negative sign coming from since I reverse my equation. Okay, so after I reverse it, I'll get what I wanted partially. I wanted that on my product set, but again, what did we just find out? I had another 2 as a coefficient, you know, as I planned earlier, right? So we probably can add all equations up and then divide it by 2. Then you do that, then you'll be able to find out, yes, we are getting, we will be able to cancel out all the rest and then getting the final equation as needed. Okay, so then that's for that. Now we'll do that operation. Okay, so as I said, now I'm gonna add equation 1, equation 3, and equation 4. Equation 2 really doesn't because I already reversed equation 2. Okay, so if you think about it, okay, so after I added all of that, I'm gonna divide whatever I add up, then divide by 2. Okay, after you do all of that, you will find out you are getting this equation. Okay, and then we should do the same operation, right? So we'll be adding this, and this all up and divide it by 2. Okay, so that's how I can get to the final answer. Delta H of this reaction, the final equation I'm looking for will be negative 108.7. Okay, so then that's my answer. Kilojoule per mole. Okay, so then this Hess law, right? So this type of question for sure you need to know what to do. Okay, so then let's look at the next question. Next question, we go, what's this? Okay, so then let's look at it. You are given with the reaction equation. You're given with enthalpy change for direction. You're also given the enthalpy formation for each substance, right? For each, you have this product given, and you also, let's use a different color. Okay, you also have this rectangle. You're given with those 2, and it's asking us about this. Okay, and then you go, oh, I have that. We don't know. Okay, if you don't know, think about it. Okay, so think about for iodine. Okay, so in under standard conditions, iodine it does exist as solid. Okay, so enthalpy formation for that for iodine solid is what? It's gonna be 0. Okay, so that's something we mentioned in your lecture. Okay, so then you go, okay, I know that. I know 2 of them. I'm looking for the rest, the last one. You go, I think I know what to do, right? Okay, so we're using this relationship. Enthalpy change of direction will equals to the sum and sum up. Okay, don't forget to multiply the coefficients. We're in multiplying the enthalpy formation for all the products. Okay, each product multiply its coefficient, add them up, minus, and the sums up about the reactants. Okay, so enthalpy formation for each reactants multiplies coefficient, add them up. Okay, so now we do the calculation. And then for this question, we do know what's the enthalpy change for the whole reaction that's given from the question. So then that's why I put it right over here. Okay, and then product, I have silver that's used as silver bromide. Use that color. Oh, I don't, let's do. Okay. Okay, so now have negative 100.4 kilojoule per mole, and I have 1 mole of it. Okay, 1 mole of this silver bromide. Okay, and then for iodine, as I mentioned, that's gonna be 0. So then that's my about my product. Okay, and then my reactants, what do I have? Silver iodine, that's what I'm looking for. So I don't know what that is. It's 1 mole times the enthalpy formation of AgI, that's what I'm looking for. And what else is there? I have the bromine, okay, which is given. Oh, the color gonna get too close. Okay, I'll just use blue. Okay, so for that, and then this is gonna be positive 30.9 kilojoule per mole. The coefficient is 1/2. So I do that and then do my calculation. I'll be able to solve this unknown right over here. Right, so that's what I'm looking for. Okay, so all of this, I'll be able to find out enthalpy formation for silver iodide. Oops. Hold on. Did I? Products minus reactants. Yes, I did it right. For a second, I saw that otherwise. Okay. Anyway, so then yeah, you solve for this, you'll get negative 61.8 kilojoule per mole. Yep. Okay. Let me just use orange as products. That's 0. Why the top up? Reactants. Let's use blue. Reactants, that's what we're looking for. And the other reactants, we have the value from here. Yep. Okay, so that's all good. Okay, and then you solve for it, you are able to get to the answer E as electron. Okay, and then let's look at the next question. Next question is about, there's also one of the multiple choice I mentioned I will ask you, right? So it's about at the standard heat of formation, how to express it, as is that we need the product to be 1 mole. Okay, so if you still remember that 2 is going to be wrong, that's going to be wrong already. 2 of the options are gone. Okay, the other criteria or the definition for standard heat of formation for a compound now be you need a constitute pure constitute elements. Free elements exist in nature at the most stable state and under the standard conditions. Okay, so then which means right, oxygen is one of the constituent elements. Okay, so it exists in nature as oxygen, not as ozone, not O3. So that's wrong. And then if you look at E, we need sodium, we need oxygen and hydrogen, not the hydroxide ion, because that's wrong. Okay, so then therefore C is our choice. Okay, so again, pure definition, right? Should be very easy question. Okay, so that's for that. Now let's look at next question. Next question is telling us we have 100 ml of sample, 0.3 molar of sodium hydroxide, and then 100 ml sample for 0.4 molar of nitric acid. When you see this two, you go, I know I have, for those two, I have a reaction. Okay, so then let's write down the reaction. And this reaction is at what? Acid base neutralization reaction. Okay, I got salt and water. Okay, so that's my reaction equation. Then you go, now what? I have before when we're looking at the example question, I give you a similar type of question. Right? So for that question, you actually have equal moles of the acid base, and now we know it's 1:1 ratio. So they react perfectly with each other in the sense that they'll react stoichiometrically perfectly. So they will consume each other, completely neutralize each other. Okay, so in this case, we quickly recognize this one has 100 multiplied 0.3, you can get to moles. This is 100 multiplied 0.4. It is still 1:1 ratio, so then you know what's going to be our limiting reagent, right? So sodium hydroxide is going to be our limiting reagent, and then your nitric acid will have left over. Okay, so then again, when you do the calculation, if you run this situation, then you know, right? Your calculation should base off that sodium hydroxide because that's our limiting reagent. Okay, so even though, right, even though you didn't notice that, but if you read the continue to read the question saying we have both initially had 35, the temperature of the resulting solution with that, and determine delta H of the reaction in the units of kilojoule per mole of the sodium hydroxide. Okay, I actually the question pointing that out for us anyway. Okay, so but again, we also should be able to understand why we're gonna use sodium hydroxide anyway because that's our limiting reagent. Okay, so that's all the background story, right? We should know. Okay, so if we know that, and then now let's think about for this question. Okay, so again, it's in coffee cup this, right? Clearly that's a coffee cup calorimeter. Then we know we have Q of the reaction, which is the reaction happens between sodium hydroxide and nitric acid. Okay, so the Q of reaction will equals to negative Q of the calorimeter, right? Okay, The calorimeter, I'm sorry, the Q of the surrounding in this case is actually the solution. Okay, so the solution itself is water. Okay, that water is not this water. That water is only small amount resulting from this reaction, but that water I'm talking about is that solution. Okay, the solution will be right that actually most the solution in that solvent we have, and then that's our surrounding. And then the solution, look at the question, right? We can treat it as what? The density and heat capacity of dissolved solution, we can treat it as the same as water. Okay, so then that's that background information we should realize. Okay, so then if we know that, we know Q of the solution, we should be able to calculate, then we'll be able to find out Q of the reaction. Okay, Q of the solution will be MC delta T. So since we're treating it as water, then we use everything about water. That water is not water just from the reaction. Okay, so that's for that. Then this water is how much? Okay, so then if you look at people, I don't have a mass of water, but look, we have 100 ml of that, 100 ml of that. So when you put those two, that's 200 ml. Again, we'll just trade it for water. Okay, so then that's what the mass will be. What? Let me put that. Okay, so that'll be 100 ml plus 100 ml. We know the density for water is 1 gram per ml. So then that'll be 200 grams. Okay, so then that's how you get the information. Okay, so that'll be 200 grams. Specific heat capacity that will be given for this specific question. We didn't give it to you, but then that will be given. Okay, so I'm using 4.84 joule gram degrees Celsius. Okay, and then what else we know? The temperature change, right? So the temperature change, if you read the question, the final temperature minus initial. Okay, so the final is 37. Initial for the water is 35. Okay, do this calculation, I got 1673.6 joules. Okay, so then that's the heat of the solution absorbed, right? So that's a positive value. Okay, so now we know our reaction is releasing heat. Okay, but now let's continue. Set this up. Okay, so then you'll have Q of the reaction will equal to negative 1673.6 joule. This is from what? This is from, right? That's limiting reagent, so we can calculate based off sodium hydroxide. So this is coming from 100 ml of that 0.3 molar of sodium hydroxide. Okay, and then can we calculate how many moles that's for that much heat, right? Okay, so you calculate that, you multiply and divide it by 1,000, you get that's 0.03 moles of sodium hydroxide. Okay, so basically that much heat is coming from 0.03 mole, but we wanted to know every 1 mole, right? So then that's what our question is asking. Okay, and then, but the other part, you go, okay, I got that moles of sodium hydroxide. Then you go, what about this enthalpy change? We're calculating heat, but then that's another thing about coffee cup calorimeter, right? So we know it's also delta H enthalpy change will equals to heat of that reaction. Okay, so since it's a constant pressure. Okay, so then they'll equal to each other. So then let me use this color. Okay, so then it will equal to negative 1673.6 is coming from 0.03 moles of that sodium hydroxide. Okay, do this calculation, we'll get negative 55.7 kilojoule per mole sodium hydroxide. Okay, so then you can what was it? Yeah, you can finish the choice, and then it's gonna be A. Okay, so anyway, I was also gonna say if you use 4.18, you get negative 50. So for that, I got actually for this when you use 4.14, you get negative 55.787. So if you round it, that's gonna be 55.8. Okay, and then if you use 4.18, you get negative 55,733. So then you can round it just for 8. Okay, so then for example, don't worry, I'll give you the specific value. Okay, so I'll just if I'll just put it on our equation paper 4.184. So we're all using 4.184 to do the calculation. Okay, so then we're gonna be on the same page. Okay, so then just for the information. Okay, so then that's 17. Okay, so now let's look at the next question. Okay, the next question is about more calculation about coffee cup calorimeter. Okay, so if you look at this question, this is type of question we actually did multiple times. But again, I just want to remind you, and we actually did this type of calculations in the lab. We literally we define what's the specific heat capacity first and no matter. Okay, so then that's pretty much the same situation, but that's really they can. Let's look at it if it's in our inferior, how we're gonna solve it, right? So 45.9 grams of metal heated to 95.2, and then placed in a coffee cup calorimeter contains 120 grams of water, specific heat capacity, and then giving the temperature, initial temperature, and then saying the final temperature of the water is 24.5, as we said, right? So we know that's a hidden information, right? The final temperature of the water will equals the final temperature of the metal will equals to 24.5 degrees Celsius. Okay, and then now we can set up the relationship in the sense of heat of the metal will have the negative relationship with the heat of the water. Okay, so then we can set this up and then plug in the information we know. Okay, so then let's do that quickly. Let me get myself, let's get some space in here. I'm gonna move this up front so we can do that. Okay, so for the metal itself, we know we're gonna use MC delta T, everything about the metal, right? Okay, we're gonna use all the information for the metal equals to negative MC delta T, everything about water. Okay, so now let's plug it in. So I have 45.9 grams times, we don't know, that's something we're looking for, and temperature change will be 24.5 as we figure out initial temperature for metal is 95.2. Okay, and don't forget a negative sign, otherwise it's totally gonna throw everything off. Okay, the mass of water is 120 grams, specific heat is 4.18 joule, gram degrees C, temperature change. I'll be final minus initial, so it's 24.5 minus initial is 21.6. Okay, have everything, just one unknown, then we can solve for it. After you solve for it, that will be B as boy. Okay, the last question, very similar. Now instead of looking for the specific capacity, we're looking for the mass. Okay, so then that's the difference. So then let's look into this question. Okay, so we're given with the mass of the aluminum, we know the molar heat capacity. Okay, slightly different. Okay, so I'm gonna look into it with you. Okay, so it's heated to 82.4, drop into calorimeter, and then water is that, initial temperature is that, the final temperature, I believe I don't need to say it one more time, right? So the final temperature of this aluminum and the water is gonna be the same, and asking what's the mass of the water inside the calorimeter. Okay, so then that's what that is. The relationship still gonna be the same, right? Okay, so that's heat of the aluminum will equals to negative heat of water. Okay, we're gonna use the same relationship. Now let's see how we're gonna set this up. Okay, so we'll have heat of we're gonna use mass of aluminum, specific heat capacity for aluminum, temperature change for aluminum. Okay, and equals to mass of water, we're looking for it, specific heat capacity for water is given, temperature change for water, that's also given. Okay, so those are things given where we know we're looking for, so then that's set this up. Okay, so again, the mass of the aluminum is 32.5 grams, and specific heat. Now what do I do, right? Okay, so I have a 24.03 joule per degree C, and it's a mole. You go, I don't know, I never seen this before, but let's set this up. I believe you've seen this, right? You know what to do because we're looking at heat. The unit's gonna be joule. It's everything else we need to cancel out. Temperature change, we have that. Okay, the temperature change was what? Temperature change for aluminum is gonna be initials 82.4, final is 24.2, 82.4, right? Okay, so that's the temperature change. Then you go how that degree C go cancels out. But that gram per mole, how can I cancel that out? You go, I know how to cancel that out, right? How grams and moles are related to molar mass. Okay? So you just need molar mass. I'm going to use a different color right here. So then you see that's what I'm doing over there. Okay, so then molar mass of aluminum, you go to periodic table. Then you go, okay, that's 24.03. And then change it to in there. Okay, so that'll be 24.03 joule, sorry, not joule, grams per mole. Gram got cancel out, mole got cancel out. Now we just get joules as we want. Okay? Again, I'm trying to remind you, even though, right? Yes, I didn't give you this tab before, but you will still be able to figure out just based on the units, based on the knowledge you have already learned. Okay, so that's what I'm gonna tell you about. Okay? So anyway, so then this will equals to the negative about water. The mass of water, we're trying to look for it. We don't know. Specific heat capacity is 4.18 joule gram degree C. Then we can use the temperature change. Then we're going to solve it. Okay, temperature change will be final minus initial. That final temperature 24.2 minus initial 22.3. Okay, do all of this calculation, you'll be able to find out the mass for water. That turns out to be 212 grams. Okay, so then this about this question. Again, just want to show you the little difference than what we can change or we can do, but then you still know what to do. Okay, so that's the end of this video and thank you for listening. Hopefully this is helpful.